are going to take a model of a simple pipe with these dimensions, and the material of this particular pipe is having an Young's modulus of 30 E6 psi and length of 120 inches. Now what we are going to do is we are going to perform buckling analysis on this particular pipe. See here, according to the theory, the critical buckling load P dash is equal to K into pi square EI by L square, where K is the constant and this particular K is dependent on the type of boundary condition. So in this case we are going to fix one end of this pipe and we are going to leave other end of this pipe free. So for that particular boundary conditions case, we are going to have a value of K equal to 0.25, and once we substitute all these values into this particular formula, we are going to get the critical buckling load, which is 65,648.3 pounds. So now what are we going to do is we are going to solve the same problem inside ANSYS Workbench and try to find out whether this particular theoretical buckling load and the buckling load that is obtained from the ANSYS Workbench are same or not. To perform buckling analysis on that particular pipe, I have opened ANSYS Workbench. Now I am going to take the static structural, drag and drop it on the project schematic, and once I drag and drop it onto the project schematic, I am going to double click on the engineering data, and here by default structural steel is applied, and in the problem also this particular pipe was made up of structural steel, but the Young's modulus is 30 E3 psi. So for that purpose what I am going to do is I am going to go to the units. I am going to change the units to US customary, and once I change the units to US customary, then I am going to go to the units tab and I am going to press on this display values in the project units. So what happens, until now we have seen all the quantities in the units that we have defined, but when I change it to this particular option, what happens, the workbench is going to show all the units which are default units inside ANSYS Workbench. So for example, if I have given the Young's modulus in MPa, it is going to show in MPa, but if I have selected the option to display in project units, which you can get here, this particular workbench will be showing all the values in the default project units, which is right now US customary. So now the units have changed. From here I am going to change the Young's modulus from 4.17 to 30 E6. So I am going to go to the units once again and I need to select other US customary, which is this particular unit system. So I am going to select this unit system and I am going to change this particular Young's modulus to 30 E6 psi. And don't worry, it is not going to change the default value of the stored material inside ANSYS Workbench. So you can just close the engineering data, and once you close the engineering data, you are going to right click on the geometry, say import geometry, and you can select this pipe. Then once you have selected the pipe model, you need to double click on the model cell. Then once the ANSYS mechanical has opened, I need to apply the boundary conditions and loads. So what I am going to do is I am going to go to the mesh and I am going to say generate mesh. You may ask why you haven't changed this particular selection, as the default selection for this particular body will be structural steel material. I need not change the value. And once I have generated the mesh, what I am going to do is I am going to right now just right click on static structural, say insert, go to this fixed support, and I am going to select this particular face and I am going to apply the fixed support. And once I have selected this particular fixed support, I need to apply the force, and remember this particular force should be compressive force in order to decrease the stiffness of this particular structure. So I am going to right click on the static structural, say insert, go to force, and once I select the force, I need to select the face on which I need to apply the force, and I am going to select this face. I am going to press apply, and instead of vector I can change it to components, and in the components you can see here that this jet direction is in the axial direction of this particular pipe. So I am going to select the jet component, and in the jet component I am going to give the value here. So In the first case, what we are going to do is we are going to apply a load of 1 pound and then we are going to solve the buckling problem and we are going to find out the buckling load factor. So I'm going to give -1 as this load should be in the negative direction. So if I'm giving it in -1, it is showing upward direction. Then you can just change it to 1. Once I've changed it, now I have applied the force in the required direction, which is the downward direction. So I'm going to right click and say solve, and once I solve this particular problem, I'm going to check the stresses and deformations that is going to occur inside this particular body. Because we have applied a very small load, we don't have much stresses or deformations. So what I'm going to do is I'm going to right click, say insert, go to deformation, and I'm going to go to directional deformation, and as I've applied the load in z direction, I'm going to select z axis here, and I'm also going to right click, say, then I can right click and say insert, go to the stresses, and I can select the equivalent stresses, and I'm going to right click and say evaluate results. So once I have evaluated this particular results, you can see the directional deformation is somewhere around 6.3 minus 7 inches, which is very small when compared to this particular length. And here the equivalent stresses are around 0.187 psi, which is very less than the tensile strength of this particular material. Now in the next lecture, I am going to show you how you can perform buckling analysis on this particular pipe using ANSYS Workbench. Finished performing structural analysis. I am going to close this mechanical, and I am going to just drag and drop this eigenvalue buckling analysis, and I am going to drop it on the solution cell of this static structural. And once I do this, all the required data will be transferred from the static structural system to the eigenvalue buckling analysis system. I am going to double click on the setup cell of eigenvalue buckling so that ANSYS mechanical would open again. So see, once the ANSYS mechanical has opened again, now we got access to these two systems which are a part of the coupled analysis. The first system is the static structural system, and the second one is the eigenvalue buckling system. Now we need not do anything, as you have applied all the loads in the static structural. You need not apply any load in the eigenvalue buckling, and you can just directly right click on eigenvalue buckling and press solve. So don't worry if the solution has taken time. In comparison with the linear static structural analysis, the buckling analysis will take more computational resources as well as more computational time. And once this particular solution is done, I can just click on this solution branch, and here I am able to see the load multiplier. As we have seen in the theory, in order to find out the critical buckling load, what we need to do, we need to multiply this load multiplier into whatever the load we have applied here. So the load here we have applied is 1 pound, and I'm going to go to this solution branch, and here the multiplication factor is 65,600. So what happens at a load of 65,600 pounds, you are going to have a buckling mode of this particular structure. According to the theory, we have got the value of around 65,648.3, which is very much nearer to this particular load value. Then we are going to change this particular force into 10,000, and we are going to perform the buckling analysis once again, and we are going to find out the load multiplier in this case also. For that purpose, I am going to go to this force, and I am going to change it to 10,000, which is 1E4, and I am going to resolve the total problem once again. So once the static structural has solved, I am going to right click on the eigenvalue buckling, and I am going to press solve. So once the solution has completed, I am going to select the solution branch, and here I am going to see the load multiplier. So the first load multiplier is 6.56, which multiplied with this particular force we have applied, which is nothing but 10,000, we are going to get 65600. So this particular value is the load value at which this particular structure is going to buckle, and we were able to verify that the result that is coming from ANSYS Workbench is nearly equal to the value that we are going to get from the analytical method using the formula of a critical load equal to K into pi square EI by L square. So this is how you are going to perform buckling analysis inside ANSYS Workbench. In the next lecture, we are going to see how to perform a buckling analysis on a crankshaft. Problem, we are going to perform a buckling analysis of a crankshaft. This particular crankshaft is made up of structural steel and a load of 300 psi is applied onto this particular face, and here there are these two fixed ends. Now we need to find out the critical buckling load for this crankshaft as well as the buckling modes for this crankshaft using ANSYS Workbench. On that crankshaft, I have opened ANSYS Workbench and I am going to drag and drop the static structural. Once I drag and drop the static structural, I am going to also drag and drop eigenvalue buckling, and I am going to just drop it on the solution cell of the static structural. As this particular crankshaft has been prepared by structural steel, we need not change any material. So I am going to right click on the geometry cell and go to import geometry, go to browse, and I am going to select the crankshaft. Then I am going to double click on the model cell in order to open ANSYS Mechanical. So once this ANSYS Mechanical is open, as this is a coupled analysis, we are going to have access to these two systems. So one is the static structural system and another one is the eigenvalue buckling system. So now what I need to do is I need to change the units to this US customary, and once I have changed the units to US customary, you can just say right click on static structural, say insert, go to this fixed support, and you need to fix this particular face as well as this particular face, and I am going to apply. And once I have applied these constraints, then I am going to right click, say insert pressure, and I am going to select this particular two faces, and I am going to say apply, and I am going to apply a pressure of 300 psi. So I am going to just enter 300 psi. So once I have entered the required value, now what I need to do is I need to solve this particular problem. Now here, instead of finding out two modes, I want to find out 4 buckling modes of this particular crankshaft. For that purpose, what I am going to do is I am going to go to the analysis system in the eigenvalue buckling, and here I have an option known as the maximum modes to find. In this I am going to set it to 4. By default this will be set to 2, so that if you are going to leave it to default, you are going to find out 2 buckling modes. And once I have changed this particular value to 4, I am going to just select 2 systems and just click on solve, so that what happens, the static structural will be solved and then eigenvalue buckling will be solved. So once the solution is done, I am going to click on the solution branch, and here I am going to find out the load factors or load multipliers. See here, instead of 2 load multipliers, I was able to calculate 4 load multipliers. This was because I have changed the analysis setting and asked the computer to find 4 buckling load factors instead of 2 buckling load factors. In general, we can calculate any number of buckling factors, but what happens if the particular body is subjected to the first buckling mode, it is going to fail. And if we want to study the further behavior, it is known as a post buckling analysis. Coming to the values here, we have both negative load multipliers as well as the positive load multipliers. So if you want to find out the buckling load, what are you going to do? You are going to take the value of the applied pressure here, and then you are going to multiply with this particular load factor, and then you are going to get the value of the critical buckling load in mode 1. Likewise, if you are going to multiply the pressure value with this one, you are going to get the critical buckling load in the mode 2, likewise mode 3 and mode 4. So then coming to the positive values as well as negative values. So what happens? A negative buckling factor means that the particular structure under consideration will fail if the load direction has been reversed. So for example, instead of say applying this particular load in this direction, if I change this direction, then what happens? This structure is going to buckle in mode number 1. So if I reverse this direction, let us say instead of applying like this, if I just apply it towards the outside, this particular structure is going to buckle. Likewise, see, getting a negative buckling factor is not a error. It is always possible. For example, if you take pressure vessels, if you take water storage tanks and other sorts of examples, you may have lot of number of negative buckling factors. So what happens is, it is up to the CA engineer to define whether this particular buckling factor is going to be useful or not. So for example, in our case, let us say always if the load is applied only in this particular direction and I don't have any change in the load direction, then I can just ignore these two buckling factors or load multipliers, and I can directly go to this particular mode and I can see whether it is going to buckle or not. Likewise, if I say there is an reversal of the load direction, then I need to consider this particular load multiplier as well. So depending on the type of problem, depending on your situation, you are going to select whether you are going to take up this negative buckling factors or not. And remember, negative buckling factors are not bad. They are always possible. You want to find out the buckling mode of this crankshaft as well. So what I am going to do is, I am going to just select every buckling load multiplier, and I am going to just right click, say create more shape results. And once I click on create more shape results, I am going to get this in the form of deformations inside the solutions branch. What I am going to do is, I am going to right click, say evaluate all results. And once I evaluate all results, here in the graph area, see, this is going to represent the buckling load factor values. So as the load factor values, first two load factor values are negative, it is showing it on the downside of the axis, and these two are on the upper side of this axis. So if I click on the total deformation one, I can find out in this particular mode, this is going to take this particular shape. Remember one thing, whatever the values you are going to get from linear buckling analysis, we have to make sense of only the load multiplier as well as this shape. You cannot find out the direction of buckling using this linear buckling analysis accurately. In order to find out the direction in which this particular structure is going to buckle, you need to be going to nonlinear buckling analysis, in which you are going to use the large deflection theory as well as incremental steps of load will be applied to characterize the behavior. But this particular linear buckling analysis is important to find out the buckling load factor and to estimate whether this particular structure is going to work or not. So I can just click on any of these particular modes, and I can just animate those modes and say in which shape it is going to buckle. So once I've done all these things, I'm also going to check whether this particular object is going to fail under static conditions. So what happens, I'm going to just right click, I'm just going to right click, say insert, go to stresses, go to equivalent stresses, and I'm going to just right click, say evaluate all stresses. So once I evaluate the stresses are around 383, but the material can withstand a load of up to 3E7 psi. So we can say that this particular body is not going to fail due to the static conditions. So this is how you can perform buckling analysis using ANSYS Workbench. In the next lecture, you are going to see how to perform a thermal buckling analysis on a bimorph using ANSYS Workbench. We are going to perform a thermal buckling analysis of a bimorph. So what do you mean by thermal buckling? So if the structure is going to buckle only due to the temperatures that are present inside this particular body, then we can say that this particular body has been subjected to thermal buckling. In this particular problem, we are going to open the already solved thermostructural analysis problem of a bimorph, and then we try to find out the buckling temperature for this particular bimorph using ANSYS Workbench. On this bimorph, I have opened ANSYS Workbench. Now what I am going to do is, I am going to go to the file and I am going to restore the archive in which I have saved this thermostructural analysis of the bimorph, which I have done earlier in this particular course and saved. So I am going to press on restore archive, and it is asking me where the archive is present, and I am going to select this particular bimorph archive, and I am going to press open. And once I ask it to open, it will ask me the location where I can save the extracted files from that archive file. So I'm going to select this desktop, and I'm going to save it on my desktop. And once I save this particular files, ANSYS Workbench will open all the archive files. Once the workbench has opened all the files, then what I'm going to do is I'm going to perform thermal buckling analysis now. So you just need to go to this eigenvalue buckling analysis, drag and drop it onto the solutions branch of the static structural analysis system. So what happens here? This particular thermal loads have been transferred to the static structural, and in the static structural we haven't added any structural loads. So what happens, whatever the stresses and strains that are produced inside this particular body are due to the temperature differences or the temperature loads present inside this particular body. So what happens now, I am going to transfer the same loads to the eigenvalue buckling analysis system, and I want to find out the critical temperature or perform the thermal buckling analysis. Once I have transferred all the data, I am going to just double click on the setup cell in order to open ANSYS Mechanical. So once the ANSYS Mechanical has opened, see, we have access to the three systems which are present in the coupled analysis. We have both steady state thermal analysis, static structural analysis, and the eigenvalue buckling analysis. So now what I need to do is I just need to say solve everything. So I'm going to just click on static structural, and I'm going to click on eigenvalue buckling also, and I'm going to solve this particular problem. So now the solution is done, and I'm going to click on this solution branch, and here I am able to see this load multipliers, and here also I have got one negative load multiplier as well as one positive load multiplier. So what happens here, the stresses and strains are only due to the temperatures that we have applied and the internal heat generation we have applied. So what happens, these temperatures are the boundary conditions and this is the body conditions. In order to find out the buckling heat generation, you need to multiply this particular load factor which you have obtained here with this particular internal heat generation, so that you are going to get a value of internal heat generation at which the buckling of this particular bimorph occurs. So what happens, if you are going to perform a structural buckling analysis, you need to perform a static structural analysis in which you are going to apply all the required loads and then solve the static structural analysis, and then take this total results into eigenvalue buckling analysis and find out eigenvalue buckling. So coming to the thermal based buckling analysis, what you need to do is, first of all you need to perform the thermal analysis, and then you need to transfer this particular loads into static structural, and from there you need to attach the buckling analysis system and you need to perform the thermal buckling analysis. That is one thing. And another thing is, you can directly apply some thermal loads inside static structural analysis, and then you can convert then you can take all these values into buckling analysis system to find out the buckling modes inside eigenvalue buckling. So with this we have successfully finished our course, and thank you for joining me in my course.